All right, last presentation or demo of the day by Rafael Polanco and Piyush Mehta. Implementation of NNEF, Neural Network Execution Framework, as a pseudo on-orbit demonstration.
Great. Thank you. Thank you. We need to show this. Let me go through. Okay. Thank you. Okay. Well, we can share your screen. Yeah. Okay. Well, thank you everyone for having here. We really appreciate all of your support and having the opportunity to present this framework. So we are very happy and proud to show our updates in our neural network execution framework. So first of all, I would like to show an outline we wanted to present. So we wanted to expose our motivation and the research project that lead us to create a general framework for the execution of the neural networks. So first after that, we wanted to show a quick review of what we showed and what we have in the last version of this workshop. After that, a brief explanation of our architecture improvements and since then and how all of this is working right now, and show what we recently made as a hardware-software integration in a small hardware test, as we can see here in this part, in order to simulate what would be a realistic spacecraft-like environment or configuration. So in this environment, we are going to show several neural networks made in different platforms that is going to run in this configuration and with our own framework. So after that, we are going to show a performance comparative between this configuration and versus a regular computer, and of course the next steps in our project. So for a better explanation of what is our research project, I leave you Dr. Piyush Mehta, who is leading the project. Thank you.
Thank you, Rafael. Make no mistake, Rafael is the star here, as he was last year as well at this demonstration. I merely am going to talk about the project, motivation, and overview in a very high-level sense. So the fundamental motivation behind this project was the desire, as we saw in the keynote yesterday, the desire to observe the sun from different vantage points. This includes the 360 view, including potentially polar missions. But what this requires is new technology that can allow us to actually transmit the data that is collected from missions that go to these vantage points. A very popular modality for observing the sun is imaging, and that requires, when you're talking about deep space missions, transmitting that data back down to ground is a major challenge. So one of the primary goals that we are trying to tackle with this project is bandwidth limitations and data compression. There are primarily two components of this project. One is, like I mentioned, the algorithm development, AI-based compression algorithms. And in the next few slides, I'll kind of give you a very high-level overview of where we are in that component. But again, the focus of this demo is the second part. How do we actually go about executing or inferring, doing neural network inference on mobile platforms like satellites? And so when I was writing this proposal, my group was divided. Some students preferred TensorFlow, some students preferred PyTorch. And so that led to this idea of potentially developing a generalized framework where if your neural network is trained or developed in a given framework or a platform, then how can we actually allow, or how can we develop a framework that can do neural network inference with minimal overhead, right? So that's really the gist of this effort here. So in the next few slides, like I said, I'll cover where we are with the algorithm development side of things. So this is a very high-level overview of the traditional, conventional data compression algorithms versus neural-based compression algorithms. The key components are the same. You have some form of encoding followed by quantization and then entropy encoding. You have some form of transform followed by quantization and then entropy encoding. And then the reverse process takes place on the ground once you've transferred the string down to the ground station. The big difference between the two is that for a neural-based compression algorithm, the training of the transform, in this particular case, which is done using autoencoder, happens in an end-to-end process. And so when we are executing this model on a spacecraft, as you can see, there are different components that need to be executed. A lot of the encoder operations are convolutional, as not surprisingly, I guess. And so what we see here is one of the algorithms that we've developed. And the primary requirement here is a trade-off between rate and distortion, right? And that's achieved using this Lagrangian parameter lambda. So higher the bit rate, lower the distortion, and vice versa, right? And so it's an optimization problem where you're trying to optimize and minimize the bit rate, hence enhancing the compression ratio while optimizing the information that's retained. And so in the context of distortion, we've tried several different kind of loss variables. One is the standard reconstruction loss, then we have perceptual loss, and then we also have adversarial loss. The surprising part, and somewhat counterintuitive to me, was the adversarial loss actually did not perform as well as we expected. The plain attention network actually performed much better than an adversarial network. But so this is, as you can see, this is a very high-level overview of the network. It's highly complex, and so that makes it a challenge to actually deploy this on a spacecraft. And so my last slide before I hand it back to Rafael, this is where we're currently at. So we have this model trained on level 0 data. We have two images, one on the left, that's the original image. On the right is the reconstructed image. But on the left, the table shows the table with the metrics. We are able to achieve a really good compression ratio, close to 750, 800. That is significant. So if I give you a benchmark, today's compression ratios on missions are typically about a factor of 2 to 4. We are bettering that by a factor of 2 to 400. While really minimizing loss. So this is obviously lossy compression. What currently goes in most operations is lossless. And so we are able to achieve really good PSNR ratios at really low bit per pixel rates, and then really performing well on the structural or perceptual metrics of MSSIM and LPIPs. With this, I'll just hand it over to Rafael to go over the demo.
Yeah, thank you. Well, as commented, our SwRI project, a continuous development in deep learning algorithms, drive us to generate a neural network framework to execute the inferencing process in our networks to run that in a flight space software. So our premise is integrate virtually any type of neural network, no matter what is the framework that we wanted to use or was used to develop and train those neural networks, and get rid enough of that framework dependency in the spacecraft. So, of course, all of that to run in a light hardware software environment, as this one, and execute that only using C or C++ code in a light or / real-time operating system. So yeah, so this is our previous version that we presented in this workshop. But that time we only show this running in a regular computer, running in CFS and in a Linux Ubuntu virtual machine. Back then we have we showed a vanilla convolutional autoencoder that read sun images of the sun in 3 different wavelengths. That was the input of the encoding part of our model. Of our encoder model receives those images in 3 different channels. With that, these images were encoding and that creates this latent vector. This vector is going to be as well sent to the ground station, and this ground station processes the images to send back the images again to recover that. So this was a version whose architecture was very basic in that time, because in order to do that, we needed to create a regular CFS application to this network. But if you wanted to create more neural networks, switch with another one, or create more neural networks, you needed to create more CFS applications. And well, we obviously needed to work with that for this version. And back then, even we were using a previous version of this famous handshake between Cosmos and the CFDP engine and the CF application in CFS. So we managed to get a new version of that. So this is our architecture right now. So we create. So now with this framework, we can claim that the framework is more open and generalize it to execute any type of neural network, and everything starting only starting with a single point command sending command to our device, where we can parameterize the specific network that we wanted to use, its inferencing characteristics, as for example the dataset size, the batch size of the batch size that we wanted to create for this processing, and the reserved memory for each inference elements, the output elements that we wanted to generate. That is very important because, as you know, for small devices we have small portions of memory, so we wanted to take care of that, so we can control how much memory we wanted to use for this specific neural network. So in this version, we implemented a new design pattern that allows us to simply manage all of the execution of neural networks from a single point that is called the NN Manager application, that is very general. That is regular CFS application. But the contribution of our framework is to manage that you can create more neural networks, you can integrate more neural networks without the necessity to create more CFS applications, only to integrate it more layers of code. For example, we can create an abstract layer for each type of neural network that you wanted to integrate, and you can integrate concrete libraries for each type of neural network framework that you wanted to manage. For example, you can create one concrete library for PyTorch, one concrete library for TensorFlow, as go on. And with that, obviously you need to, as long as this framework have the possibility to create there's neural networks in a scripted format. This is very important because this script format is going to be sent to the spacecraft, and this script is only to be executed using C or C++ code. So we wanted to maintain our, sorry, because this mouse is not moving it. Okay. I don't know why this is moving very weird, but well. Sorry, this is not working. Okay. I don't know why, but well, so, yeah. So we want to maintain this framework open. So for that, we are only accepting binary inputs, and we are generating binary outputs. So it's responsibility of the implementation of the neural network to manage all of these inputs, convert that normally to tensors, and the tensors are processed into these concrete libraries. And after that, you can generate, again, binary information to send back to this information to ground station. So we're using for that the interaction between for this implementation, the interaction between the Cosmos application in the ground station and the CFF component. It's very important to mention that from the beginning, this framework was conceived as to be not dependent on the flight software system that we wanted to use. For this implementation, we are depending or relying on CFS, but we can migrate all of this implementation, migrate to, for example, F-Prime or whatever framework that is in the market. So it's very important to understand that our framework is independent of the flight software system. But for this specific implementation, we are depending in these components of the CFS, for example, for sending commands, to receive telemetry, to send telemetry, to receive commands, and to save all our inferences information in the storage device through the DS component, and send this information to the ground station. Okay, so so here we have we set up a small satellite or configuration to test our framework, to have a realistic space mission hardware configuration or small sat. So with that, so in this device we install the flight operating system. We install one instance of CFS, our neural network execution framework, as well as 3 networks. So being one of them, the result of our research project that Dr. Mehta already mentioned some slides before. So for the sake of time, we already upload in this device all the models, and we need to assume that all the inputs, data sets, or images are stored in the storage device. So let me show you this. Hopefully this is working. Okay, yeah. So this is the device. Let me show you. I'm going to change to, okay. I have here 2 connections to the device, 2 SSH connections to that, and we have here the Cosmos application already that is ready to send commands to the device, and we have here as well. With this, our telemetry window that is going to receive the telemetry of our component of the framework. So let's move on and let's start the CFS application. I am pretty sure many of you know this CFS application starting, and let's start the telemetry of the telemetry process in the spacecraft. So right now, already start. So okay, everything is ready for our neural network inferencing. Okay, let's move on. So okay, so we wanted to show 2 types of neural networks. The first of all is what is called MNIST convolutional autoencoder. It's a very easily developed neural network, but we are integrating in this network two flavors of that. One made in TensorFlow, and the second one made in PyTorch. So we are all integrated the encoder part into the spacecraft. So we have here these two models. Can you see here? Okay, I wanted to point this. Okay. Right now we can see here these two scripted models of the encoder part of this neural network, and we have here two specific implementations, each one corresponding to the specific platform. This is for the PyTorch, and we have here the libraries that is called Torch libraries. We have here the encoder part of the TensorFlow, which is using the CPP-Flow libraries. And with that, we can simply execute the compression part of the neural network, generate what is called the layering vector, and send this vector again to the ground station. So this is one of the neural networks in two flavors, and the third one will be what was mentioned by Dr. Mehta. This is one of the complex neural networks inferencing, and this network is working exactly in the same structure as the previous one, but this network is much more complex than before. It's more resource demanding, and this is why this framework is using, this network is using additional libraries that manage some complex algorithms, and that was quite challenging for us because we needed to integrate those libraries in such a way that these libraries could be read in our original implementation of the network and in the TorchScript version of the model. So yeah, that was very, very challenging. So okay, so let me show you a small demonstration of how all of these networks are running into the spacecraft. So right now, okay, so now let me show you that all of the models are in the spacecraft. These two models correspond to the encoder model of the MNIST convolutional autoencoder, the first one, and the second one is the compressor that will be managed our neural network. Important to say that the second one is made for processing sun images. Sun images is going to compress that and generate again the images in the ground station. And let me show you here now the version of the TensorFlow model. All of those models are scripted versions of that in order to execute this in the spacecraft. And we have here all of the data sets. I'm very sure many of you know these data sets of the images. And lastly, we have all of the sun images that are already in the spacecraft. So with that, also I wanted to point there is nothing in this moment in the folder where we are going to generate all the inferencing information. So okay, so let's start with the demo. So I am starting with some command to prepare the save of the information, inferencing information in this file, in this location. So I am starting here the first network. So let me show you this. So right now we are seeing that this framework, this model is already started. We are processing 400 images, and I am putting here only 2 or 3 examples of that, and everything runs well. Okay, so after that I'm going to execute. I'm going to show here in this window we can see the model, our component is telling us that we generate 400 images, and we are showing here the last of these inferenced elements in the framework. Okay, so let me execute the next one. Then, okay, the next one. So this is our inferenced second process. So this is going to take a little longer because obviously this process is much complex. It takes more length in memory, and we have only 8 images. Meanwhile, let me show you the data folder that we already showed. So right now there is one file more, and let me show you here. We'll wait only some seconds. This is going to be executed. Right. So we have 8 images processed, and finally we're going to process the final process. So right now we have in the spacecraft. Okay, both of them were combined in the same file. It doesn't matter. So with that being said, we generate all of this information in the spacecraft. So we wanted to return to our slides. So that being said, right now to close the loop, we need once all of these files are compressed files are sent back to the ground station, we can process them in our normal framework. In this case, this is PyTorch. So I structured this file to simply get all of the information in a new tensor. With that, you can simply process them in the decompressing process. We get again all the images. And the third process, and for the second model, we are processing here the 400 images with the same structure. So, well, to finalize, we are showing here, this is our numbers for these networks. You can see here, for example, that obviously in the spacecraft, the performance will be lower than in a regular computer, but it's enough to process science information or science data. For example, we can process 2,000 images per second for the simple model, but for the second one, that is the complex one, we can process roughly one image per 5 seconds. So we can generate one image every 5 seconds of that. Okay, so well, we demonstrate that we can run neural networks in small devices, as a small sat. For the next step, we wanted to deploy this in a real-time operating system. We wanted to deploy in more advanced hardware boards and deploy this in a diversity of spaceflight softwares to increase our mission applicability. So, well, that's it. So I am open to questions.
Yeah, there are a few questions.
Yeah.
There are a few questions online. The first one, how does the compression time and resource used for your NN-based compression compare to the traditional
Could you repeat
compression?
That? Yeah, could you repeat that again, please?
How does this compression time and resource compare to the traditional compression algorithms?
Well, we have here.
If I'm not wrong, this is more about the compression algorithm.
Correct.
Yeah, we don't have that information in the presentation, but you can find in the reference that I have, the paper that's published. We've done the study for the performance.
All right. The second part of the question is the autoencoder lossy or lossless?
It's lossy.
It's lossy.
And if it's lossy, how did the input-output images compare?
That's what the metric.
That's what the metrics?
Yeah, that's what the metrics show.
All right, very good. You can follow up with more details. Next question, when integrating the PyTorch abstraction, how did the binary size increase? How much? Sorry. How much?
Size of what, sorry?
The binary size increase when you were integrating PyTorch.
Okay, I guess they are talking about how much is the information compressed. Okay, the information is compressed about in a fifth part of the original information. So the compressed part is a fifth, 20% of the original one. I don't know if that's a question.
They're asking how big did how big did the executable size get?
How much? Sorry.
How much bigger did the executable code get?
The executable code.
The executable code get.
Oh,
the model, I think.
We can see that in the yeah, I understand the question. We can see that on this part. You can see here, this is the scripted version of the autoencoder. So this is not clear enough. And this is the PyTorch. This is the PyTorch version, and this is the the TensorFlow version of that. I don't know if that answered the question. Yeah, okay, yeah, thank you.
All right, next one is, could you explain a bit more of abstract factory pattern applied to the creation of the
Yeah, of course.
fiber?
Yeah, I was very quickly, sorry for the bad explanation of that. Yeah, of course. Yeah, this is I was applying a normal abstract factory pattern for this. And yeah, you needed to implement, we have a manager that is acting as a gateway manager. Is the only point of entrance of this framework. But below of that, you will work with an abstract class. For example, imagine you have a neural network that is processing this neural network compression. You have only one of these, but if you wanted to implement this in TensorFlow, you can implement this concrete class. If you have another version that is working with the same network but with PyTorch, you can have another concrete implementation. So on. So many versions of you have of this neural network. On if you can work with different versions of the network, but with the same abstract interface. So this is a abstract factory pattern. So with that, this framework allows us to not create more CFS applications if you wanted to integrate more neural networks. So in that manner, you can create only one framework to integrate whatever networks you wanted to have. You can have 20 neural networks or 30 neural networks working in the same package.
Very good, thank you.
Yeah, exactly.
Are there any questions? I have one more online.
Yeah.
What is, you may have pointed to the size, but it's related to what's the actual memory footprint of the software that you were demonstrating? You were showing some slides. I don't know if it answered the question.
I don't have this information. The footprints in the memory, I don't have this information because I needed to see the process.
Yeah. You can follow up with Slack and with more details.
You can even see on live demo with the memory, how it's working the memory. But this memory in any moment goes for more than 4 gigabytes. This device has 8 gigabytes. Was never stopped.
At the top.
Yeah.
Very good. Thank you.
Yeah.
Thank you very much.
Okay. Thank you.